So for the last 10 years, I've worked in the proprietary derivatives trading space. You might prefer to think of that as high-frequency trading or HFT. August the 1st, 2012 was a watershed moment in our industry. On that day, one of the major players, Knight Capital, effectively ceased to exist after a glitch in their IT systems saw them lose $440 million in 45 minutes. That's the rate. Now, inside the industry, this incident is pretty infamous, but even outside, it's pretty well known. So I remember the kind of commentary from the IT peanut gallery in the weeks after the incident as the analysis became public. For those of you who don't know, a technician had failed to update one of 8 instances of an application with a new version which had repurposed an option. Within my company, almost invariably, the commentary focused on the foolishness of repurposing the option or the poor operational practices that kind of led to the missed update. Within my company, management, which still included the company founder, had one question: what stops this happening to us? Our honest, humble, and terrifying answer was also simple: luck. So Sawyer's rockets have a fantastic reliability record, at least by rocket standards. With over 1,700 launches since the 1960s, they've really become the workhorse of the International Space Program. No, manual. Oh, no. Oh my goodness. This is just what I was talking about.
That's what you get having a VB back there.
Yeah, true. Oh, maybe I should turn that off. Yeah, let's turn that off. Oh. So on October 11th of this year, an ISS recrew mission went wrong during launch due to a booster anomaly. Now, amazingly, Sawyer's had safety mechanisms for just such a possibility. So what happens is the crew module detaches from the launch vehicle. It's what they call, quite poetically, a ballistic descent. So basically, you take your rocket ship, turn it into a cannonball. So the crew were recovered with no significant injuries. Now, that's a testament to some great safety engineering. Oh, no, it is the macro. No, not that one. PowerPoint experts, macro window, shortcut. Yeah, that's what I was afraid of. All right, let's try it. Come on. All right, so compare that outcome to that of Challenger from 30 years ago. So what I want to talk about today is safety engineering for IT, by which I mean engineering for situations that we realize may arise without knowing how, and despite our best efforts to prevent them. I'll talk through some of the principles and share my observations and reflections on the journey that our company took as it moved towards more of a culture of safety. So I've used the word safety here as a bit of a catch-all. The immediate association is with, obviously, physical safety, and that's where all the real-world examples come in, but I'm going to use it in a broader sense to include things like financial, legal, reputational, or information protection. Think of it as the counterpart to risk. So while the systems we built were entirely specific to trading, and I'm not going to go into any detail about them, I think there's some generality in how we went about it, and it's applicable to any business where there's a lot at stake. So after giving management cold comfort that we wouldn't follow in the footsteps of Knight Capital, we took 3 avenues of remediation. First of all, we looked at how we were testing in both approach and thoroughness. We were already in the process of improving in this area, but we really doubled down on our efforts. We set stronger expectations of what we were testing, and we invested a lot more in testing infrastructure. Second, we looked at some of our software designs, and we looked at ways of making them simpler, both in terms of implementation, but also feature set. We also looked at how we managed failures, and for a lot of components, we moved to a fail-fast methodology. Don't get fancy with trying to recover, just shut down. Finally, we introduced dedicated control systems. So the purpose of these systems was purely to detect and manage unexpected situations. And so that's where I'm going to focus on this talk today. So there's another way to look at this. We can rephrase these three focus areas. Testing aims to improve our reliability, to reduce the likelihood of things going wrong. Design aims to improve our resilience, to expect that particular things are going wrong and to manage them gracefully. Controls, on the other hand, are about safety, to manage situations that we didn't expect to be in. So if there's a problem that we know about, then we generally aim to engineer it out or to test it out to make sure that it doesn't occur. If there's a problem we know of that we accept that we can't prevent, then we generally design resilience around it. But sometimes all bets are off. Unexpected situations happen, and we still need to manage them. So software developers, by and large, are well versed in reliability. We explicitly teach students about testing. We grill people in it in technical interviews, and there's a whole body of expertise that's built up around it. With design, I think modern architectural approaches have got us really close to commodity solutions for really good resilience. But I'd still say it's the preserve of at least the experienced journeyman. But our experience when it came to safety was that nobody had really good feel for it. None of our developers, and I include myself. So the biggest challenge for safety is hubris. So by definition, safety scenarios arise from unexpected and unforeseen reasons. So as software developers, we're very familiar for ensuring that a system works the way we expect it to. And we can also imagine situations and work through how the system will respond in those situations. It's another thing, and it's quite unnatural, to start thinking about the behavior of a system with something going wrong that you can't know. So engineering hubris leads us to believe that we have thought of all the scenarios. So the Titanic, engineered to very high standards, famously built with resilience against sinking. And yet when disaster struck, it was the safety systems, the life rafts, that were found wanting. Now, some of you might scoff going, life rafts, pretty fucking obvious. But remember, hubris is the enemy of safety. So as a result of the Titanic disaster in 1915, Woodrow Wilson signed the Seamen's Act into law. It contained a provision requiring retrofitting of a complete set of lifeboats to all shipping. So on July 24th of that year, the SS Eastland, made top heavy by the addition of those life rafts, capsized at its wharf in the Chicago River. 844 passengers and crew were killed. That's a greater loss of life than the Titanic. So safety engineering is harder than you think, and the consequences of getting it wrong can be catastrophic. Now, I don't want to give you the impression that before we embarked on this program, that we didn't really have any protections in place, that we kind of showed up, turned things on, crossed fingers and hoped for the best. We certainly had some measures to keep things under control, but we didn't really have a dedicated, thoughtful and systematic approach. So some years prior to the Night Capital incident, there'd actually been a bit of thought about, would it be possible to sync the company with an errant trading system? So that thought experiment actually came back with a negative answer. They thought, it'd be hard to lose that much money and surely someone would notice. So I'll get back to hubris later. But first, let's just take a quick look at what I mean by controls. So broadly, controls fill one of three roles. Firstly, they can validate that the state of our system is as we expect. Might be a check that our data and database is correct, that the system has been deployed in the expected way, or that we are appropriately recording trading transactions. Secondly, a control can validate that the actions that we're taking are correct, whether that be doing something or not doing something. So that might mean checking that a trading system is generating sensible orders, or that an information service is yielding a sensible volume of information. So finally, a control system can be one that is invoked to control the problem and bring the system back to safety. So in our trading system, for example, the ultimate containment and control was called the kill switch, and it just severed connectivity to an exchange, just preventing an out-of-control situation from getting any worse. In terms of design, so controls are designed to be independent from the primary system. because they're used for unforeseen circumstances within the primary system, relying on the primary system seems a bit foolish. So orthogonality goal can be one of the hardest to design for. So by orthogonality, I mean that the controls aren't designed to just duplicate the primary system. It's not supposed to be an independent implementation of the same thing, because if you do that, you risk introducing the same blind spots. So rather, you're trying to come up with a different approach to the same problem as the control. So in the case of trading, we don't want to check that orders are sensible by having a second system look at the same parameters and generate orders and then cross-check. We instead want to have an alternative construction of what a sensible set of orders might look like and just validate orders against that. We also want controls to be simple. So design, implementation, use, and purpose. Complexity at times of high risk is a recipe for disaster. It's not the right time for subtlety. You just want a hammer. Controls are generally built with relation to a system, not a component. It's self-explanatory. And finally, you're aiming for a minimal set of controls. You're trying to minimize complexity and cost. So what we found was that designing controls with these constraints was actually quite hard, and it's not a familiar sort of exercise. People are generally used to thinking through a problem, but with controls, you're sometimes thinking around the problem. So there's obviously quite some overlap between controls and monitoring, but I think there's some differences, and it's worthwhile drawing some distinctions. So monitoring often arises as an intrinsic byproduct of the primary system. So when you think your technical monitoring, like latency, capacity, and throughput, they're interesting and useful, sure, but they don't really fall into the domain of controls. Functional level monitoring, I think, has a lot more in common. But controls also have the ability to take direct action. So something that pure monitoring is generally not designed to do. So the main difference is that controls are designed as extrinsic systems with capabilities of performing real actions. So I hope that fills in a bit of detail about what I mean by controls. The next question is when to invest in them. So investing time into safety is different to investing in reliability and resilience. Reliability and resilience efforts are about helping the enterprise achieve its mission. So the value of investment relates to the cost of unreliability. Safety, on the other hand, is quite different. Safety systems are for when the risk or cost of executing the mission becomes too great and that you want to abort the mission. You want to man the lifeboats. You want to turn the rocket ship into a cannonball. You want to hit the kill switch. Now, engineering is a discipline of making informed decisions to reach optimal outcomes. But optimality is defined by the client and not the engineer. So the impetus needs to be driven by a well-informed client. So in some cases, particularly where it's a physical harm situation, the impetus is obvious. In other cases, where it's more financial or reputational, a lot more nuance is required. It's also the case that optimality isn't stationary. So a startup company, particularly with respect to financial risk, warrants a very different safety profile to that same company once it's become established and has more at stake. So for this audience, there's probably some of you working for larger companies thinking, well, this stuff is routine. Doesn't everyone have this? There's probably some of you working for smaller companies where you're thinking, actually, I just want to spend time getting to a point where I've got something to worry about. But hopefully some of you are making the transition, and you're the target. So economically, investing in safety systems is like insurance. There's a negative expected value. But the intent is to safeguard against unaffordable losses and not everyday losses. So as a general rule, if you expect investing in controls to save you money, you should be investing more in resilience and reliability instead. So in our case, the Knight Capital incident prompted the management team to talk about the risks of operational failure of IT systems, because before Knight Capital, we'd never properly deeply talked about it. Management thought that they were actually running a low-risk business. They had mature, tight controls on market risk, and they understood that really well. IT never really thought about it. We were just focused on making the next dollar because that's what our traders were asking us to do. But when management realized the existential threat posed by IT system failure, their response was clear. Before Knight, the IT priority was to get into the market, availability. That was the priority. After Knight, The priority was safety first. So I recommend a deep conversation on this topic with your clients before you get your night capital moment. And if you don't think you've got risks, remember that hubris is the enemy. Okay, so I've talked about what safety controls are, why you might want them, when to invest in them. From here on, I'll talk about the challenges that we found when trying to introduce a safety engineering approach and some of the successes and failures. I'll predicate, sorry, the number's no longer updating, but it's probably up around 100 million by now. I'll predicate this part by saying that we didn't start with the framework of reliability, resilience, and safety that I've kind of talked through. That's entirely post hoc rationalization. So when the word came through that we needed to have control systems in place, we took our standard approach of developing in IT. We handed requirements to the dev team, they built some stuff, we deployed it, made sure it looked like it was okay, and got on with our lives. We then conducted some internal audits. And by audits here, I don't mean we got some guys in suits with clipboards and checklists. We actually got internal experts from within the organization. Now, the company's a bit odd in that it's a global organization, but the 3 regions run entirely independently to the extent that no technology is shared. Now, the upside is that you get 2 peer organizations that exactly understand your business, but have come to their own conclusions independently. Even better yet, one of them is Dutch. If you've worked with Dutch people, you'll know that it's a national sport that they will tell you how rubbish you are. They've got a saying, if it ain't Dutch, it ain't much. So as you can imagine, the assessments showed up all kinds of flaws. So the simplest way to explain where we went wrong is probably to say that we focused on technology at the expense of people and process. Which is to say we built some tech and just moved on expecting everything else would follow. And that was a big mistake. We completely missed the human element. A good control isn't just a bit of software, it's a whole set of human processes that go around it. A control gets invoked for unforeseen reasons. It's exactly the scenario where you want a human in the loop. And those humans need to know what to look for and what to do. So a few examples. It became clear that the understanding of exactly what the controls were for and how they worked and when to use them was pretty patchy. So we needed to put much more effort into education and to really streamline the process around how we wanted people to behave. Then when we quantified some of the risks with respect to the control settings, the results were gobsmacking. So we had introduced a pre-trade limit system to prevent the kind of damage that an errant trading system might do. When we back-tested some failure scenarios against those limits, we found losses in the billions. So the tech worked, but it was completely ineffective because we didn't really have people thinking about what the problem was. We also found that we treated our control systems as just like any other, which is to say we gave them a best effort kind of treatment. Doesn't look like it's on fire, it's probably okay. Now, for control systems, this mindset can be particularly problematic because they can be called on quite rarely, but when they are called on, they really need to work. So we needed to be much more proactive around these systems. So we started blind fire drilling. We got a lot more aggressive in our functional monitoring. We regularly reviewed controls and we established and reported KPIs. So it generally took an additional year of process improvement and control refinement before the controls actually got good. So one useful approach was to explicitly differentiate between true positive, and false negative events. So each case points to a different problem in the system. True positives, where the control was required and it was activated, suggest you've got a reliability or resilience problem in your primary system. False positives, that's the boy that cried wolf, suggest that some usability or education is maybe required in your control, or that maybe it's a bit sensitive. You don't want to get into a situation of alert fatigue. And then false negatives, where the control was required but not activated, suggest you've got a real problem with your control, and that might be technical or it might be cultural. So after our initial subpar effort, we took a closer look at the governance and accountability around our controls. So initially we had developers build controls and just left them to it. It's the model we use for most of the system, where developers and traders work pretty closely together. It's totally kind of bottom-up driven. The problem is that developers are expecting to move on to the next thing, but the controls require eternal vigilance and thought, even when they're not being activated. So our approach was to have specific accountabilities for controls assigned to management, something that we ordinarily didn't do. So the very simple model we used for accountability was to consider how the organisation would respond to three simple questions about each of the controls. What is the control for? How does it work? And the third one, which is the kicker, how do you know it works? So only when we were confident that we could answer these questions did we consider a control to be effective. Now I realise that there's a huge body of work out there about standards on this stuff, but it takes a lot longer to explain to people than this. So as a rule, our developers didn't particularly enjoy working on controls. Remember that controls have a negative expected value. They're really designed to protect the company owner's owner's interests. Now with remuneration linked to company profit, that actually puts control work at cross purposes. We tried to specifically incentivize control through the remuneration system, but it wasn't particularly effective, and I think that's because we used a stick approach rather than a carrot approach. The bigger factor getting appropriate behaviour was just through resetting the cultural norms about how we work. Similarly, a bit of control fatigue set in. Controls aren't exactly fun compared with the auto trading algorithm. So after the program had been running for a few years, we found it difficult to maintain motivation. So exacerbating the incentives and motivation problem is that the controls took real patience to streamline. It's difficult to build technology and processes for situations that are both unexpected and rare. We found initial versions of the controls would generate too many false positives and would require further refinement because we really didn't want to get into a situation of alert fatigue. So it really did take at least a year of practical experience to get a control halfway right. And I'm not sure that there actually would have been too many shortcuts. Getting mature controls really just seemed to take time. Now, as a developer, it's pretty common to refine something as it gets used more and more. It takes a lot more patience to refine something as it gets used less and less. Now, I think a key part to making the endeavour work was the very clear top-down directive to make it so. This is in a company which is ordinarily run by people at the coalface. So for a period of around 3 years, our automation risk program was one of the key focus areas for the management team, and everybody knew. We had senior people deeply engaged. By that I mean regional CTOs, the CRO, heads of trading, and lots of domain experts put significant effort into thinking about the problem. So it certainly wasn't cheap. I think it would have been a big mistake if we'd just hived off a new unit or a new department and given them the problem and asked them to solve it. Instead, we targeted the whole organisation. Now, the three-line of defence model, which is popular for assurance in finance, can be misconstrued as being that there's a control department and risk management's their responsibility. It's totally the wrong way to go about it. Establishing good risk and control frameworks requires deep engagement from all stakeholders. So wherever we strayed from that approach, we got a worse outcome. One of the biggest drivers was a focus on the risk culture of the organisation. So making the switch from get into the market to safety first is a big and difficult change, particularly where remuneration is so closely linked to trading profits. In terms of everyday activities, we revamped how we followed up with incidents. We became much more thorough in our incident documentation, and we followed up much more on actions. We also started taking some of our key incidents and subjecting them to much more in-depth incident reviews. And we invited the head of trading to come along to those reviews. So significantly, we didn't invite the people that were proximally responsible for the incident. Instead of doing that, we invited their managers. Now that gave the process a much more significant feeling. It also helped us steer clear of finger pointing, and it helped team leads really build accountability for the work of their team. These sessions were generally pretty frank, lots of difficult but not unfair questions, and started getting people to really think in a safety-first mindset. So there's a lot of good resources out there about how to review incidents. It's worth looking at some and looking at how you're doing it yourself. Once we started getting better data capture on our incidents, we were also able to look systematically across it to see common themes. So we could see things like configuration complexity, market opens, failure handling as common factors in a lot of incidents. So that told us where we needed to be more cautious and apply more thought. And we asked our teams to rethink their approaches around these areas. Now, over time, my feeling is that there hasn't actually been a decline in the number of incidents. But the bar for making something an incident has gone way down. So we're much more concerned about what goes on. We also have seen a shift in incidents from realized losses to opportunity costs. And I think that's a shift in the culture going from get into the market to safety first. So we also introduced specific training on both risks and controls to make it clear to people coming into the organisation exactly what was at risk and how we wanted them to behave. So prior to the program, new starters were kind of welcomed in. We gave them the video on market mechanics, gave them a tour of the code base, handed over the Auto Trader manual, and kind of pointed them at Jira. As a result of this program, we established a much more systematic training program. So we had people come in, we gave them specific training on incidents, on controls, and on risks. One second, please. Oh, I've lost me. Let's just skip. So I certainly am not going to claim invulnerability in the company. I've learned the hubris lesson. But I'm fairly confident that the likelihood that we'll sink the company today is much less than it was before we started this program. I think the work that we've done on the controls has not just reduced the likelihood of the big one, it's also improved the efficiency of handling everyday incidents. So we're able to identify stuff going wrong sooner. We've got better tools for dealing with it, and the team is much better drilled on how to respond, but it hasn't been cheap. So at the outset of this program, one of the hopes was that a strong control framework would allow the development team to move faster. With the system protecting the company against catastrophic loss, maybe the primary system could be engineered to more pragmatic standards. Particularly for us, availability isn't the key metric. So the idea went around the business quite a bit. On one side, we had people kind of waiting for the development velocities to materialize, but on the other side, we had people being very critical whenever a control was tripped. Now, it's the second group that won, and I think they're right. So introducing the control framework risks creating a moral hazard situation where people take on more risk because they think it's been offset somewhere else. But the possibility there is that you end up with a net increase in risk, which is exactly what you're trying to prevent. So we've made triggering a control a significant incident that warrants detailed follow-up. So that's kept the engineering at a high standard, and we insist that our developers don't build making assumptions that the controls are going to be there. So an additional win is that by becoming more aware and stricter when things are not quite right, we've been able to drive improvements in our reliability and resilience engineering. Remember that the idea of safety systems is for the unknown unknowns, but tripping a control turns an unknown into a known, and that gives you the opportunity and the chance to identify it and to remediate it. So I'll wrap up here with a brief recap. So I talked through safety as a distinct practice from reliability and resilience, some of the control design principles, and investment guidelines. The key driver for us was taking a top-down, whole organisation approach. And I think after a bit of a false start, we learned to put people and culture before the technology. But we still found that in some respects, it just takes time. So I think we ended up with a safer system, and while the primary benefit is insurance against catastrophic loss, there's been some wins for reliability and resilience as well. And that number would now be 250 million? Cool, thanks.
Thanks, Matt.